Yo, party people, welcome. My name is Dr. James Utley, and I'm here to give you part two of my presentation. If you didn't know, I was presenting on the Creator Stage 5 at Defcon 33, and there was a problem with the slides, and so it made for a really rough time to present with no slides. So we're going to replay it, rewind it, and do it again here for my folks over at Biohacking Village. So let's get into it. The title of my talk, you'll see, is Bio-Cryptography is the Game-Genie in a Post-Quantum Dystopia. Now, if you don't know what a Game-Genie is, this is it. This was a key to hacking games in my childhood, and that's why it all stems from this great idea of the Game-Genie. So you'll get it as we work through this presentation, but remember, the Game-Genie. And also, I always thought this was such a funny company because it was named Galoob. They don't name companies like that anymore. Anyways, next slide. This is who I am. I am this skulled individual. My name is Dr. James Utley. I have a PhD in health science. I have the honor and privilege of being a chief scientific officer at Origins, which is a stem cell clinic located in Panama City, Panama. So check out Origins. I founded this little aggregate of crazy bio-futurists called Syndicate Laboratories. And again, that's an homage to YT Cracker, if you didn't get it. So anyway, I spent a lot of time in the Navy, and so like as I was saying, I'm a professional scientist during the day, and at night I'm a biohacker extraordinaire, or whatever you want to call it now. I see that it's like they've been shopping around this term called biopunk, which is cool. I'm down for that as well. And I am officially a registered member of the Transhumanist Party. So if you don't know what it is, check it out. All right, moving on. Here we are. But before we begin, we need to talk about something that is truly important, which is AI. AI is everywhere. It's permeated every piece of any type of technology that I touch as now being either enhanced or degraded by AI. So the fact is that it is a technology that will change, that is changing everything right beneath us. The part is that it's controlled by these tech bro overlords, which I cannot stand. And so I always say, give AI the middle fingers. So anytime you find AI slop in this presentation, feel free to throw up the AI middle fingers. I specifically left the AI slop in here, which is like weird graphics, misspellings, weird blurs, weird all that shit. I left it right in this presentation so you could throw up the give AI the middle finger. And, if you ever see me out in public and there's people doing this at DEF CON, if you see me, give AI the middle finger. All right, moving on. Here we are. We'll start with one, right? So as I mentioned before, my talk is about biocryptography. Now, we kind of have to set the stage for this talk. And firstly, we have to understand that this talk has a setting. And that setting is that we have been totally dominated by this advancement from, when we've discovered a realm of artificial general intelligence, which is not GPT-5, by the way. And this AGI has then moved into a super intelligence where now every communication, every digital communication is now being monitored, right? So it's a real Skynet situation. And that is where the setting of this presentation, where this takes place, right? Okay, so first off, let me just back up a little bit. So we have the setting. Now let me back up with what is biocryptography. So biocryptography, it really represents a convergence of biological principles and cryptographic techniques, right? The main fundamental theme of biocryptography is it's meant to enhance security through the unique characteristics of living organisms. Like that's fundamentally the definition, right? Now, but as we're going to look at it in this presentation, right, then we need to know that we're kind of leveraging the biocryptography as it's extending to the capabilities of DNA, and so it's beyond the scope really of like this real central definition of biocryptography, and it explores DNA and it's kind of like going to delve into a novel domains of data hiding and data communication. Because ultimately, what I'm trying to design here is an end-to-end solution that we can adopt a standard where we can communicate messages through the use of DNA and positioning. DNA steganography is kind of an advanced application, but it has to be universal adoption. All right. We'll get to it moving on. So let's talk about the slide here, which is the paradigm shift. The biocryptography, we are a biocryptography in a surveillance state, right? So we have a means to communicate, which is a natural cipher. So DNA is the oldest known storage medium, and now we can use it for humans to securely communicate. Right now, there's a lot of researchers that are really looking at the storage capacity of DNA, right? But what I focus on here is how we can communicate by encoding messages in DNA. All right, now, so as the slide mentions, there's a biological security layer. It's like, so without knowing the exact primers, you can amplify the correct sequence, creating an uncrackable wetware-based firewall. And that's a fancy outline. Those graphics that are the box graphics are kind of the futurist prototype of what we'll get to at the later phase 2 of the BioCypher later in this presentation. But the whole thing is we have to understand that we're integrating DNA into information security, and it's kind of a shift from the conventional data or even broader biometric approaches. So DNA, as I mentioned, is recognized as the oldest natural storage medium, and often it offers precedented capabilities for information processing and storage. The emerging discipline, often referred as DNA cryptography or DNA computing, harnesses the unique chemical biological properties of DNA in sequences to construct sophisticated cryptographic systems and ensure a high secure data transmission. The key is it relies on complex math problems. So like traditional cryptography relies on complex math problems for its security foundation, but DNA cryptography is unique in that it capitalizes on the inherent complexities of DNA and how we can manipulate that process for biological process through these intricacies, the intricacies of encoding, synthesizing DNA, preserving DNA, amplifying that DNA, sequencing the DNA, meaning decoding, and ultimately to decode a message and or information. Now I understand that this is an ambitious project, and there's stuff that we'll go through that is already in the realm of it exists in real life, and then there's phases that we're still very much a prototype. But let's make sure that I'm not missing anything on the slide here. So hard to hack, harder to track. DNA messages can't be intercepted like digital packets, right? As you can imagine, they require a physical like a physical vector, a physical way to store it and move, and it also requires equipment and domain knowledge and all of these things, which are then kind of more. There's physical barriers also, which also cause a big pain in the ass in being able to do it. All right, and remember, this presentation is in the post-survival humans, and we're in a world where AGI monitors all digital bytes. And so this DNA cryptography is our only means of survival and communication. Okay, moving on. Okay, we kind of talked about this slide here, and so maybe you can already see the AI slop in there. I'll focus on this. It is DNA or DNA storage techniques, or the ability to communicate with DNA as a medium, and hopefully on a standard protocol that the ultimate concealment, it is an ultimate concealment medium, which is 1 gram of DNA could theoretically store 215 petabytes of data. So that's really dense, right? So unprecedented density. So density, durability, parallelism. Okay, so low power consumption. DNA computing requires no external power once biochemical reactions are underway. Of course, plug it in. Extraordinary durability. Data encoded in DNA can last for centuries, which is really crazy, and that is definitely longer than any maintenance conventional media. You can have massive parallelism, to be doing something in parallel, and that's biochemical operations can occur simultaneously, increasing computational speed. So it's more than one thing. and I think that also makes it more difficult to interrupt or hack. And the long-term storage potential, right? DNA attributes suggest there's a future standard of DNA storage and secure communication. So you could embed encoded message and/or data in an item through using DNA, and then hundreds of years later, you could then retrieve it and sequence it and then decode the message. Okay. And here you can see that. There is a lot of AI slop here, giving that AI the middle finger. And anyway, it's really the essence of what we're trying to achieve is encoding digital data into data sequences. Now, I have some notes here, which I want to make sure that I do not miss. Some fundamental concepts that are on my notes. So I'm going to check it out here because I'm in the privacy of my underground layer and not on a stage. And it really talks about, I would like to talk about this for this slide, so maybe it's not 100% related, but steganography or DNA steganography or the techniques, right? So substitution, insertion, encryption, and integration. Like once digital data is encoded into DNA sequences, various steganography techniques are employed to embed and conceal it within a cover into the DNA sequence. The primary classical techniques utilized for this purpose include all the ones that I just mentioned. So the substitute phase involves modifying specific bases of an original DNA, undercover sequence based on the content of the encrypted message. For example, a particular message might dictate that the corresponding base remains unchanged, or that is substitute within its components, within its complement. This process often leverages a pseudo-random permutation of the base and controlled by a secret key to randomize the locations where the message is embedded, therefore increasing its the ability to be detected. So that's a lot. That's a lot there. But we're going to move on to the insertion phase, which involves directly inserting the secret message of the DNA sequence into a covered DNA sequence at predetermined random locations, which is more of like what I'm about is generate a message, encode it into DNA, which we'll get into in the later slides, and then decode it or have the ability to decode it. I think the take-home point here is that the process of message retrieval and decoding, there's precision in it, right? So you have to have the origin and where those type of pieces have to be in place, and then there's precision, which is AKA known as pain in the ass. Where we're gonna move on. We just talked about concealing information in DNA, and now we're gonna get to the main meat and potatoes of this presentation, which is the BioCypher. So the BioCypher, as you can see that in the slide there is some straight Skynet shit going on there, which means that they are interrupting all the digital communications, and BioCypher is here to help. Okay, for just like any good presentation, we're always going to start in the middle. So what I mean by that is as I mentioned earlier, that there is parts of this presentation that is actual reality, like it exists, right? And we'll get to it, which is in phase 1. Now, there's phase 2 and phase 3, which are really conceptual at this point, which means that as more people start working on this and we're getting this thing launched, we're probably going to find a better solution, one that's more efficient, one that's more practical. All of those is the good starting point, and we're going to go through it. So first off, we're going to talk about the BioCypher device. Okay, so before we talk about this device, we just need to make sure that we highlight a few things. One is I am known for placing DNA isn't normally there into shit, right? Whether it's bacteria, whether it's yeast, whether it's mammalian cells. Take the DNA or the plasmid and then place it inside, right? Now, that is ultimately what we're trying to do, which you'll see is we take a message, we encode it to binary then to the nucleotides, then we may order a plasmid, order a sequence of DNA, which equals the message, then take that plasmid and then place it into something. And that is the first part. So phase 1, it requires this handheld terminal device And as I mentioned, I spent a lot of time in the military, so I love these like military grade looking scary motherfucking things. But I'll break it down. So firstly is you have the encoding terminal, which is essentially the software piece of BioCypher where you're encode the message, ... It then, under a standard protocol, which that's what I'm trying to have adopted, which means adoption means you guys check it out, I open source it, you check it out, you use it, we all use it, then we got a standard, right? And we'll get into the software application part. But, so, with that is, so then it spits you out a sequence of DNA, meaning letters. Now, so you have that. Now you have to move it on to the next phase, which is in the next slide, which is synthesizing that DNA. And we're going to briefly talk about that and how that's done. But this device, it encodes, and then it has an option for decoding. So decoding is the bottom layer, which is through nanopore sequencing, which at this state, because it can be done in the field, and it's done in it is done in the field. And you'll see here, we'll scroll down, you'll see it's here on this this minion device or mini ion device, and that's how essentially that's how it's done in the field. Now there's going to be a lot of reverse engineering this device because there's really only like one vendor that sells this device, and the main complicated part is this guy, which is the flow cell. And again, there's only one vendor that really manufactures this. Now, this is like the closest schematic that I have got that I'm like, okay, well, with the right resources and engineering, then, hey, we could probably reproduce this. And if we can produce this, this is producing essentially a signal. As we go here, it's producing a signal. And if you see that it's an electrical signal, right? So you have a current running here, and you have a nanopore protein, and basically you see how it's separating the DNA there and reading it through the membrane, and then it's calculated by the current intensity on the right, which then gives you the ACT-GCT, which is your nucleotide bases. Then you're taking that sequence, then you put it back into BioCypher to decode it to the actual message. Okay, now let's go back to this. Okay, so you reverse engineer the flow cell because you don't need it to be so complicated and so intricate as this device. And I'm like a little bit simplifying this and glossing over a lot of the things, which is like, the standard library preparation and all that stuff. But I think after you mimic this or reverse engineer it to a product that you can use, and you reverse engineer this device here, which is essentially measuring a signal from electrical current, and that's what sits at the bottom of this device, which is the BioCypher device. And you see that that's a placeholder here for the cartridge that inserts, and that's essentially a high level overview of how that works. Now, because you're using a standard protocol which is messaging, then messaging turns into encoded DNA sequence, which then equals words. Excuse me, I'll take a cheers to the monster. Then what happens is you could build a standard library, a library that will help you decode the messages faster. Right? And that's the idea. It's like you get more adoption, you get kind of like some commonality, and then you get sequences that equal words, and then you could build libraries that way to make it more efficient, right? You could sprinkle in some machine learning techniques, you can have some prediction element, whether that's gradient descent or whatever to predict, and you're kind of working on nucleotide bases, which are then translating to words, which then you could predict that token. Anyway, it could get out of control real quick. But that is the essence of the encoding and the decoding of the BioCypher device. Okay, so after 2 is 3, right? So this is phase 3, right? And again, this is detached from real life because it does not exist in the real world. But I hope for it to exist, and we're going to continue to work until we can get this done. And this is a component of the BioCypher, which is I think it's easier to explain if I go to the next slide, which is a personal DNA and RNA synthesizer. So those exist. They exist. And they are microfluidic chips and cartridge-based DNA and RNA synthesizing, producing custom DNA and RNA on demand, fast, affordable, and independent, right? Which is amazing. So in theory, we can reproduce this device, find the magic behind it, or maybe work with this vendor, I don't know, and then develop something that would be more in line with the application, which is to synthesize for encoding messages, right? So optimize it that way. Now, if you can see, like in this photo here, on the right-hand side, there's cartridges there, so that's in mimicking that, you know, this instrument runs on cartridges that are pre-manufactured. So that's one step in this process is you're optimizing the synthesis part, the DNA synthesis part, and by doing that is you're optimizing the cartridges or the components of the cartridges and all of those in between to make it one, you know, hopefully an actual prototype that you could use, right? But that's the idea. So okay, so let's back this up. We're going to back it up one here. So you have your terminal. You're like, hey, you know what? I need to send a message to my friend. Here's the winning lottery numbers. Don't share it with anyone. All right. So then you're like, okay, well, let me go ahead and send this to a node, which is this, right? So in the cyberpunk future, that there's these little stations where you could just synthesize your DNA. But let's say you have this device, then you can synthesize this. Right, so then now you have your DNA, that the message has been encoded to the sequence has then been synthesized. So now you have the plasmid, right? Now, then you take said plasmid and you place it in something. And a little later in the slide, we'll have some ideas of how you could, obscure or place the DNA for transport and things like that. So anyway, you place it, or you send the plasmid to your friend. Then he's like, okay, hey, thank you, friend. I also have a terminal, and because I'm using this standard protocol, and what's going to happen is I'm going to use the nanopore sequencing, and I'm going to inoculate. I'm going to do some preparation first, right? Which we're not going to get into because it's boring. I'm going to do some preparation stuff, and then, so we'll say 2 drops of magic, and then what we'll do is we're going to inoculate the flow cell, which is this guy, this guy here. We're going to inoculate the flow cell on the inlet track, and then we're going to throw it back into the BioCypher. It's going to do its miggity magic, and then what will happen is it will spit out the coded message, which is, in this case, the winning lottery numbers, or your crypto seed phrase to, a Bitcoin wallet with, that they used to be held by Ross Ulbricht. I don't know. Okay, now we're going to get into phase 1, and then we're going to put it all together with some, practical application. Okay, phase 1. This is the BioCypher application. I love CLI tools, so I built this initially as a CLI tool. But as you can see, let's start with the one that's right next to me here, which says BioCypher. It's an advanced DNA cryptography system. It converts text messages to DNA sequences and back with multiple encoding modes. Here's the first one, the base mode, which is a simple binary to DNA mapping. Very simple. And that's what we're kind of working out now, so that we can make sure that we can decode it in a way that's, at least a little bit user-friendly. Okay, secondly is we can optimize the sequence for the nanopore sequencing, which means that nanopore sequencing, it has some limitations. We're trying to control from that by using some, by sequencing in 4s and 8s, and just make sure that if there's some problems in the sequence, meaning when it's, when we're trying to decode the sequence, if there's problems, gaps, breaks, things that just don't match up, then we have enough replication where then we can predict in between, and figure out the messages being decoded. Okay, and the last one here is AES encryption plus DNA encoding. So you're doing all the DNA encoding and mapping, but you have a password on the front, which is like an encryption, and then a password on the back, and then it uses some essence of AES encryption, which I won't really go into, partly because I'm not like a super pro at that. But anyways, it had all the commands are there, the flags are there, it's all there. Okay, so now moving up one tile, where it's like the BioCypher interactive session, so you can move into interactive mode, and it just has it has some design pieces where it's okay, encoding the DNA sequence, it shows you the statistics of the base, the properties, all of these things. And then on the right, this is something that I didn't mention, is we have to run a safety screen, right? So this safety screen takes what we're encoding, and it runs it against known pathogens to make sure that you're not by happenstance writing, you're not by happenstance synthesizing something that's bad for humanity. And I won't say it on this video or anything like that or reference to any of that, because maybe I'll get deplatformed. I don't know. And then no natural genome. So you try to like make sure that it's not like just by happenstance, that it's not like seen in nature so frequently that it would cause trouble in terms of decoding. Like you couldn't find it. It would just be too much of a needle in a haystack. And it also looks at the repetitive elements, because those can be problematic. Anyway, it gives you the statistics and the session statistics and everything. So this is the CLI tool. But I know not everybody loves CLI tools. There's a lot of people that love guided user interfaces. So we'll go over this. So this is the main dashboard of BioCypher, and it's encode, decode, and kind of how it works and how to contact us. And again, going over this shows the 3 modes here, which I showed you in the CLI tool, and then it gives you kind of the base breakdown. And this is the front end, which is a beautiful, beautiful front end on this app. Okay. And this is what it kind of looks like. And so, I mentioned like encoding DNA sequences. This is what a sequence would look like. So this would be like, hey, this is what you're going to be safety screening and copying. This is what you're going to be using. Oh, it looks like we're trying to hide the message. Where are the Epstein files? So that's what it looks like. And that's nanopore optimized. Where are the Epstein files? Anyway. And then so it shows all the statistics here. You'll see in the bottom thing where it says like the bases and and all the breakdown and the GC content, the nanopore risk score, and it just kind of gives you the, it has like homopolymer runs detected, how many like sequences are like the same nucleotide in a row, which will cause problems and be easily detected. And this is what the safety screen looks like. Here we go. And again, safety screen. You're not generating a pathogen by happenstance, and you're not sequencing something that's already a banana. And this is an example of decoding. So like, you go through all the steps and then you extract the DNA, you sequence the DNA, this nanopore sequencing, and then you bring it right back to here, your decoding step, and then you decode the message. And this message is, where's the Epstein files? So, success. All right, now we're going to bring this thing home because it's a lot. I get it. This is an ambitious project. It's a lot. There's a lot of pieces to it, and I can guarantee you that I have a tendency to talk fast and gloss over so, please, ask questions or however that's possible. We're going to make a movie right now, or maybe a movie trailer, we'll call it. And what we're going to do is, well, I guess I should say that, I spoke at Defcon 32, and everybody knows that I am such a Nicolas Cage fan. The Nicolas Cage is my jam. So I could not leave him out of this presentation. So we're gonna make a movie, or at least a trailer at least, and it's gonna be titled National Treasure: The Epstein Files, with my guy Nicolas Cage. So let's get it. And it's a Disney movie. All right. Okay, here we are. So we have this crazy scientist. He's like half cyborg, and he's been received this confidential file, and it's the Epstein files, and he's like, yo, I need to get this thing. We're in a completely we're in a monitored state, surveillance, and he needs to get this. He needs to get this encoded in the BioCypher so that he can encode it in a DNA sequence to then transfer it. Right? So, okay, he's got all the Epstein files that are then encoded into DNA. Now, how is he going to transport it? And this is for the audience, and I'll tell you what happened at DEF CON and what they voted for. The first one is, so we take the plasmid, you expand the, basically in bacteria, so you're inserting the Epstein files into the bacteria, and then you let the bacteria replicate, and so now you have an emulsification of bacteria, whichever it may be, let's say E. coli, and then you're like, okay, I'm going to spray this. I'm going to put this spray all over these plants. And I'm giving the middle finger to the AI because he's spraying it right on the terminal. But anyway, and so it's sprayed on the plants. So then he transports the plants to wherever the Epstein files are going to be decoded. in the hands of good people. They want to know the truth, and then they'll swab the leaves of these beautiful plants, sequence that data, and there you go. Now we have the Epstein files. All right. The second option is you can place it in a little bubble, or you could synthesize it in a little bubble behind that pig's ear. Just put it right subdermal in the skin there, like a PPD, and plant it like a bubble, and that will contain all the information needed. Because I mentioned DNA it's dense. It's a dense communicator. It'll transport all the Epstein files, and then you can transport the pig. Nobody will know. The last one here, which again, giving AI the middle finger, is you could transport it, plant it like a PPD, like I just mentioned, a purified protein derivative, which is used for like a test for tuberculosis. Most people have gotten it where they insert, subdermal on the top of the skin there, and it makes a bubble, but it contains that protein, that information, and that's where the DNA would be stored. And again, it's dense. So then when you get to the other side, you're probably on a time window, then you could, extract and, kind of make a, we'll just say concoction that could then be sequenced. Okay. And if you see that there's little sequencing devices here in the slides, right? Little AI slot prototypes. Oh, so there we are. So we've synthesized that here in this AI slot one on the left. And then I guess he's uploading it to BioWikiLeaks. Maybe that exists. I don't know. Maybe it will in the future. Who knows? Maybe not. But secure communication it is. And, okay, so now that's the movie. So then he returned it. He uploaded it. The whole world gets to see the truth. And life goes on. Thank you to BioCypher, which is a DNA protocol, a DNA communication protocol that is standard, that we all adopt. And now, how does it work in real life? But before we get there, I want to make sure that I don't miss anything in my notes, because I had mentioned that I had notes here. And I will say that the technical and biological hurdles of implementation, right? So let's talk about the hurdles. And we know that we've already been through all this, but it's a lack of measurability and standard protocols. So, of course, the field is in its infancy or non-existent, and it is characterized by a notable absence of standardized protocols until now, and robust methods for precise measurement across various applications. That's why I say we've landed on nanopore sequencing, because we're trying to standardize that as well. So this lack of standardization, it really hampers, makes it harder to reproduce or to provide broader adoption, right? And that's aside from the other things, which is operational complexity. DNA is working with DNA is an intricate art, and of course there's different steps, and it's inherently complex, right? We as humans are inherently complex. Now, so things that we know we have to work on is scalability and speed, and the integrity of the data, and how much data you can transport, and all that stuff. But again, we're using this as a basic means of communication. That's where it starts. And then it moves on to something grander, right? So if you wanted to do it like right now, you could absolutely use the BioCypher. You could use the BioCypher device. You could encode your message. Then what you'd have to do is you'd have to send it off somewhere to have it synthesized, whether that's IDT or synthesizing DNAs, RS, whatever your flavor is. And then you'd get it back embedded in a plasmid, and then you could do all the steps that I mentioned, and then you could decode it using the BioCypher application. Like, you could do that, right? I'm not so you can encode, you could transfer, you could decode, and then the decoding without having nanopore, you could use good old gel electrophoresis, but good luck. That seems like a pain in the ass, and reading gels, not my bag anymore. I think I'm just over it. But that's how it goes. And now we've been talking for 37 minutes, and I apologize for that. That's way over my time at Defcon. It was a great talk, and this is my contact here. Maybe here's my contact. Here's my Instagram. Scan the QR. Don't worry, I'm not hacking you, and because this is an Instagram official one. And then the next is hit me up on Signal. I'm cool with that. Again, not hacking you. And remember, it's all about the Game-Genie, and that's what started this all. I hope this has been a wild, crazy adventure, and please reach out. Check out the website, syndicate-labs.io. You'll see a little piece of BioCypher on there for a while, and how to contribute to the project. And you know, that's all. And I guess that's it. My name is Dr. James Utley. Thanks for joining me. And now we're at 38 minutes. And peace. Take it easy.